No, that's not what we want. No, we don't want that. No, I know what I look like. All right. So the idea here was that we had an index. The first thing you care about is how the index is created. So the index is created by sorting on student ID first and section ID next, right? So remember we did an example in class where you had two attributes. You sort by movie ID or actor ID or actor ID or movie ID. That means you basically have consecutively all the tuples for a single student in the leaf node, then all the tuples for the next student. So all the tuples for a student are the tuples for different, which attribute? Sections, right? So basically that is what you have. So you have, for a given student, let's say student 1000, right? For that student, you have all the tuples, all the sections for that student. So it could be 1000 section 1, 1000 section 2, up to 1000. And how many sections we said for each student? 16, right? So, well, it could turn out that, they are not numbered from 1 to 16. I'm just simplifying, assuming that maximum is 16, right? So, that's probably not really true in general because some students have few classes, some students have more. This is just a simplifying one, right? So this is generally the idea. So when you're done with one student, now you have the tuples for the next student, right? So you have, let's say, student 1001 with section 1, 1001 with section 2, etc. It doesn't have to be sections 1 and 2, but this is the information you have at the leaf nodes, and then you compress these into leaf nodes. So you compress 400 at a time, right? And then you have internal nodes that index this, and then you have a root node over that. So you have basically one root node, 30 internal nodes, and a whole bunch of leaf nodes. And every single search that you make is going to involve first looking at the root node. You will always have a root node search. Then this will lead you to some internal node here. You will always look at one internal node. And then this will lead you to some part of the leaf. And then you're going to scan the leaf to figure out how to find all the tuples you are searching for. So some number of leaf nodes. What does that mean? That every single search is whatever this k is plus 2, right? So all your searches really depends on how many leaf nodes I scan. I never go up and down, up and down. There is no such search, right? This is what we did when we wrote the search algorithm last time. So, okay, so basically this is the main question, what this k is for any of these conditions. So let's write down these conditions one by one. So one of them is student ID equals 1000 and section ID is 50. So how many leaf nodes do I have to scan to find this? Leaf nodes? One, right? There's only one tuple for a single student section, and I can really scan from your leaf to find exactly that condition, right? That's an equality search, so I should be able to do this. So cost is 3 pages, right? So I'm not going to write this from now on, but root plus internal plus 1 leaf, right? Okay. So far, so good? Now, B is the hardest one, okay? All right, so this one says, I am looking for student ID less than 1625 and section ID equals 50. Okay? What can we say about this one? So you can say I go student ID section 50, student ID 2 section 50. That's not what we do, right? So yes? Exactly, and then while you're scanning that, you're going to check the section, right? But the section ID doesn't help me reduce the number of leaf nodes, right? So I have 625 students, right? And then how many tuples for each student? 16, right? And this many tuples will fit in how many leaf nodes? Divide by 400, right? Plus 2, right? So this is what, 25? Yeah, so this is 27. Okay. Now it is possible if you are very, astute, you can say, well, actually, what if I start the range, in the middle and then go one extra, right? So it could be 28, right? I will accept both, plus minus, I don't care, right? Yes.
We can actually specifically say it's not because 1,000 is a multiple of 25. So we know it'll be beginning or end of.
How do you know that?
Because you divide by 25. We know that it's going to be exactly 25 students per day. Because 400 divided by 16 is 25.
Okay. I'll buy that too. Generally speaking, with this cost, we generally don't care 25 or 26. We generally care if it's 25 or 250. But you can say that too. Okay, I'm all right with that, yes.
Like you mentioned before, the student doesn't have exactly 16 sections.
So if it's less than 16, right, then it could be less. So generally speaking, when you're looking at this kind of cost, like for these questions, this is the logic we follow, right? But the thing that we really care is the order of magnitude, right? So like the big O notation. And for databases, the big O notation is it 1 or 10 or 200 or 10,000, right? So it's kind of, think of in terms of multiples. So, generally, it will be in the same order of magnitude, but it may be more or less. And we'll talk more about that. All right, so C, we have student ID equals 1,000, and section ID is between 6 to 6. And what's the cost of that? So how many tuples am I looking for? At most 16, right? The student may not have 16, may not have all of these 16 sections, right? But in max, it could be 16, it could be less, right? So 16 tuples in the leaf node fits in how many? How many leaf nodes? 1. All right, so 16 divided by 400 plus 2, which is 3. Okay? Because it happens that all the sections for that student are on the same leaf node, right? So again, you can say, well, we don't know for sure that they actually all are in the same. Maybe it starts on one leaf node and goes to the next. So then, in the worst case, it's 4, right? I will accept both. Okay, D. So we have student is 1,000 to 1625, and section is between 15 and 6 to 6. Okay? How many nodes will I scan? Yes?
The same as in B, because you still have to inspect the exact same number of students, so the exact same number of leaf nodes.
Exactly. In fact, no matter what I put here, right, this is irrelevant, because this doesn't help me reduce anything. I still have to scan all these students, right? So this part is completely irrelevant, so irrelevant. So this is the same as B. 27 is my answer. Okay. And finally, E is section ID equals 50. Okay. All right. What about this one? Every single leaf node, right? Because it's not sorted by section ID. There's no way for me to find individual section IDs. I have to scan the whole leaf node and then plus 2, right? So all leaf nodes. So basically this is 12,000 plus 2. Is that what I said? Yeah, 12,000. Okay. So could help if you can see. All right. Any questions? Yes.
Here's something where you have like, I want student ID in this range or in this other range, treat that as two different queries.
Right. If that was the case, you would actually probably do two different scans. Right? The question was if I had student ID in this range or in this range. In this case, yes, you would do two separate scans. Okay? So now what happens in real life is that, remember this cost, when I talk about the cost, so when we talk about the cost, we say you read the root node, then you read an internal node, and then you scan the leaf, right? So when you're done with this, you have the second query, you still have to read the root node, and then the internal node. So what happens is that the root node is very likely going to be in memory already, right? It's one node. In fact, almost all databases will cache the root of every index, right? So you never really read the root node, because that's always in memory. And often, the next level is small enough, 30 pages, that can probably also remain in memory for an index you use a lot, right? So very often, the first two levels are in memory, all you're doing is the leaf nodes, right? So that plus 2 is most often completely ignored. So because of that, ultimately it's the leaf that you care, right? It's part of the leaf. But when we are doing this in class or exams, this is kind of good mental exercise to do the plus 2. But in real life, it's almost always cached, right? So you're never actually reading those pages because they're small, which is the beauty, again, of the B tree, and you can keep it in memory. Yes?
The last one isn't 12,031, but you have to check every internal.
No, because once you find the first node, then you can follow the sibling pointers. You don't have to refer to figure out how to get there. Which is, remember that you never really have to go through the internal nodes unless it's exactly like you said, it's an OR statement, right? So in that case, you actually have two separate ranges. More questions? Okay, so there's a very important thing to remember or note in this one, okay? So the B trees are very useful, but they also have a drawback, right? So for example, it's very useful for when you have an equality for the first attribute and a range for the second attribute, right? Equality for the first and a range for the second. It's ideal for equality for both. But if you have a range on both, the second range is irrelevant, right? So this is a problem in some applications. So whenever you have two ranges. So you have, let's say, index on R, A, and B, right? Then you basically search for A is between x1 and x2, and Y is between, B is between y1 and y2, right? For this, it's actually totally useless for this part, right? So this becomes irrelevant because you can only scan for the first range. And there is a lot of applications, I guarantee you, something that you use every day that almost always relies on this. What is a tool that you use every single day? Do you use, yes? Browser, okay. Do you find directions to things? Yeah? Do you look for directions between things? Do you, when you search for something, do you kind of order things by how distant they are? Find the closest restaurant to here, and then they are ordered by distance, right? all of those basically are spatial queries, right? So generally speaking, if your data is spatial, meaning that it has an x and y axis, so each of these points are, beautiful establishments in Troy, right? So, you have, let's say this is Alibaba, this is the Union, this is Spilling the Beans. I will put maybe DeFazio's. I don't know what this one would be. Maybe this is Ilium. Okay. How about, what is that pub called? Knotty Pine? Knotty Pine here. Yeah, 15 kind of went down like this in my picture. So all of these have 2 points, x and y, right? So each of these have 2 attributes. If you were to represent them as x and y, so if you were to create an index for where these are stored, a B-tree index would either sort by x or sort by y, but often you are not interested in just 1 dimension, you are interested in 2 dimensions. So, and also, a lot of your queries will say, well, return me everything in this region, okay, which is basically a box, right? A lot of queries end up being a bounding box, within a radius of 10, would basically mean, find a box that, would be inside a circle of radius 10, and then find all the points inside. Unfortunately, this would not be very useful for B-trees, because B-trees would basically do well on the x-axis if you have an x1, but you can have values far, far off on the same, because, they are at very different y values. So, because of this, you would actually use a different index structure that generalizes B-trees that are called Atrees. So what Atrees would do is they would be exactly like a B-tree. Remember, in B-tree, you basically have ranges. You have ranges like, 1020 to 1525. If it is between those 2 values, follow this pointer. Whereas in Atrees, what you will have is you will have a rectangle, so which you will represent as, if you are inside the rectangle from 1020 to 1525, so this is 1020, 1525. If you are inside this rectangle, follow this pointer. So a B-tree basically will have rectangles for key values and a pointer for each rectangle. And you will take the space that you have. So if you had this, and you would divide it into rectangles, like this. So these are tuples. Let's call them A, B, C, D, E, F, G, H, I, J. So your leaf nodes will have basically these tuples, right? So you have 4 leaf nodes. One is going to have A, B, and C. One is going to have D and E. One is going to have F and G. And one is going to have H, I, and J. These are the tuples at the leaf nodes. The internal nodes will basically be the rectangles that I drew. I mean, they will be tighter than those. But they will be those rectangles that point to those. So let's call this rectangle 1, rectangle 2, rectangle 3, rectangle 4. So I will, for example, have here rectangle 1 will point to this node. Rectangle 2 will point to this node. Rectangle 3 will point, and rectangle 4 will point. And then you can build your R tree by taking these and then grouping them inside bigger rectangles. So, for example, you can have one rectangle like this, let's call this R5, and one rectangle like this, let's call this R6. So I can have R5 will point to this, and R6 will point to this. It's basically the same exact structure, except for instead of ranges, you are storing the bounds of rectangles. Okay? Now, R3s are very common, but they are very complex because you have to find the right rectangles to put things in. You have to group things, you have to cluster things. But once you have an R3, you can actually write other things. So one of the very common queries that we have not seen in B trees is called the nearest neighbor tree, nearest neighbor search. So, for example, in addition to finding what is inside a rectangle, so if you're doing a search, let's say you wanted to find all the data inside this search area, what you will do is you will find which of the two rectangles, R5 and R6, intersect with my search query. Since only R5 intersects, I'm going to follow this node. Then I will check if R1 and R2 intersect, then I will follow both, and then I will scan these. And if you're doing a nearest neighbor search, if you want to find the closest point to this search query, then I would do something simpler, where I basically order nodes in terms of how close they are to that node, and then continue seeking branch and bound. If you ever take AI, it's kind of an AI type thing, but you can do that with R-trees. The reason I'm talking about R-trees is that they are now very common. For example, Postgres has these generalized indices called GIST. I don't remember what generalized something search tree, which you can use to implement R-trees easily. And in fact, you can buy a spatial extender called PostGIS that has R-trees for storing any geographic data. Points, rectangles, polygons, roads, line segments, and so on. And this is all the, all the spatial queries that you use are built on as a technology, right? So generalized search indices are very common, and R-trees are very common. They are also similar to something called a quad tree, but I'm not going to talk about that right now. But all this finding direction and giving routes and so on are built on structures like this. So R-trees are useful, but they don't solve everything. Now, the other thing that you use every day with a browser or without a browser is a search query, like Google search, right? So the Google search is very, very unlike database, right? So nothing we've learned really helps you with answering, find all tables that contain some keyword, right? Because we actually index on very specific things. So to be able to really search for individual values, where those values may be stored in many different things, you actually have another type of data, which we call an inverted file. Okay? So an inverted index is very different than a B tree, right? A B tree will basically take all the tuples, and then for the key values, it will sort all the tuples, and then construct upper levels. Whereas an inverted index will do something different. So let's say you create an inverted index on attribute A. Okay? So let's say attribute A is the review text. Right? So the reviews that review text is so reviews that review text. This index is a totally useless index if it was a B-tree index, because it only searches for the review as a whole, right? The whole text. You never really search for the review with the text. You generally search for the review with the keywords in the text, right? That it contains certain words. And for that, B-tree is completely useless. Instead, what we would like to do is we would like to first find all words that are used in any of these attributes, right? So first find all words in this attribute for different tuples. So, you will have delicious, horrible, tasty, sauce, pizza. It's getting bad, worse and worse. Right? These are all the words that happen. And then you're going to basically create what's called a posting list. So every single location that these words occur in that attribute. So for example, it's going to say that in tuple 1, location 5, okay, meaning the fifth word is delicious, and also tuple 1 has in location, let's say 100, the same word. And then I have another tuple 10 has location 25, etc., etc. Whereas horrible, hopefully for another tuple 3 has on location 10, tuple 5 in location 20, etc., etc. So what you're doing is you're creating a linked list from the word to all the locations that it occurs in. They call this the postings file, where all this information is posted in this attribute. Then you store this in index. So you basically have to store this in such a way that I can find, given a word, all the tuples that have it, right? Or given a word, given two words, if I find all, for example, if I have a query, tasty and sauce, then I have to find the postings for both of them and then take their intersection, right? So often what people will do is, you will actually store that information using a bitmap. You will basically have for each tuple 0 or 1. Does it contain it or not? So first point, you have to first figure out if it even does. And these turn out to be bit and bit or operators. You following with me? You've seen bit operations, right? So these are bitwise and an or, depending on what this condition is. And then after you find the tuples that contain, then you go and search for the detailed ones. So this type of an inverted index, for example, is implemented in Postgres using Gin. And there are lots of systems that are just inverted indices. Like, for example, Apache has this system called Leucine that is just an inverted file. And which system that we use every day is a massive inverted file? Google, right? Google is a massive inverted file. In fact, one of the first reasons it was for its success was to be able to do this efficiently. So they have implemented an inverted file for the whole web, right? It indexes every single page that they have visited and the keywords that it contains. The postings are likely sorted by potential relevance or quality so that you don't have to read all of it because this could be huge. You probably end up reading the first few. And then your keyword queries are basically did operations on this. And then they take this inverted file and then store it in massive, farm of servers with lots of duplicates. So you can hit different servers for the same query. Okay? So inverted files are very important. You can have it in the database or outside of the database. And one final thing is hashing versus not hashing. Okay, so I see that you're all getting super tired. So I'm going to stop here for 5 minutes. I'll talk a little bit about hashing, and then we'll continue. Go and relax a little bit.